Thank you. I would like to start today's lecture by assigning the homework. And homework will be, first of all, what is a set number? 19. So this will be clamped two-span beam. So this is L, this is L, and we would like to find the expression for W of x that is valid for both spans. Okay, using 5 constants of integration. That is one. Second, determine the natural frequency equation. Third, simplify the expression using the double argument formula. For Krylov functions. Means k sub j 2 lambda or 2 lambda equals, etc. 4. Show that this determinant is representable as a product of 2 expressions. A product of 2 expressions. First expression being the frequency determinant for clamped single span beam. Am I going too fast? Oh. Say it again. Yes, I see. Oh, it does not. Can you please check here, because somehow I am rotating the page and it does not. I probably just pressed some wrong button. Oh,
yeah,
okay.
if you hit the freeze button, it'll freeze it.
Okay, thank you. Thank you. So this is homework 19. Please write down. Can I move up? of clamped single span beam of length L. And the second, frequency determinant of clamped simply supported beam of length L. Now, if this is correct, and I hope that you will show that this, what I'm stating here, is correct. If this is correct, then we have, I would say, stunning conclusions. Because look, please, for simply supported beam with support here, this behaves as, the frequency determinant is product of two expressions. This is connected with simply supported single span beam. This is connected with clamped simply supported beam of length L. Now here, if I have clamped, then here I have, look please, also product of two expressions. One is clamped, and the other is clamped simply supported. So first of all, we have the following conclusion, that this spectrum here, for simply supported case, I will call basic spectrum. This is a basic spectrum because this whole beam is simply supported at its both ends. And therefore, simply supported single span beam reminds us of this two span beam. Here, basic spectrum will be this one, clamped beam. This is basic spectrum. Now, what we are obtaining is as follows. Two span, simply supported and clamped beams share infinite amount of joint frequencies. And these are these ones. Okay, these they share. So that is shared frequencies. And they are infinite amount. Okay. So this you will be able to show by doing your homework. It's very, very interesting phenomenon. Now 4, we'll go to 4. Just interestingly, if I have, say, two tubes, and then there is another tube here. One tube into another. Okay? And between these tubes there is some elastic medium, say some springs. Imagine there are some springs. Okay? Continuous springs. Inside. Okay? Then, and this whole thing is vibrating. Our whole system is vibrating. This can be, for example, this could be inner nanotube, and this could be outer nanotube. And these are the forces of interaction. Okay, and the whole system is vibrating. Now, natural frequencies in this case too have interesting property. They come in two series. Okay, there are two series. So that means that there is, say, first series and first frequency, second frequency in first series, third frequency in first series, etc. And then first frequency in second series, second frequency in second series, then third frequency in second frequency, etc. And this, of course, is infinity, so that is infinite series, and this is also infinite series. That means that if I take frequency, say, frequency domain, and I'm taking some large interval of frequencies, then 2-volt carbon nanotube has twice, or approximately twice, as many frequencies as a single volt carbon nanotube. Okay. Now let us, that was just a side comment. Not more than that. Let us come back to these two span beams. And we may need the whole page. So let us denote the first frequency. So we will denote the modes. Okay? How the modes are behaving. Mode shapes. Okay? So that is the first mode. Okay, now that is a second mode. Sorry. That is a first mode W1 in first series. So that is W2 in first series. Okay, and then that will be so that is W3 in the first series. Now here will be, that is W1 in second series. So this behaves as if support is inside. So these things are as if support entered inside. Okay, and it is simply supported here, and simply supported there. So it behaves like this, and this. Now here will be like this. First frequency, clamped here. Now maybe I should take smaller amplitude. Now this will be yes. Okay, that is W2 in second series. And there is third. Okay, W3 in second series. Okay, so that is how the system. So, and all of these modes are belonging to this two-span beam. Now let us see what happens what's clamped when we have two-span clamped beam. Okay, here situation will be, okay, so that will be the first series, W1 of the first series. Oh, sorry. No, I did not make, that is not correct. First of all, it should start here with clamped. This is clamped, simply supported, like this. So this, then second. This is clamped here like this. One. Okay, so that is W1 of second series, W2 of first series, W2 of second series, W3 of first series. Now if you compare, now we will try to compare somehow. Okay, this mode shape, clamped, simply supported. And here we have clamped, simply supported. So this is actually, if you cut and paste, you will see the same, absolutely the same pattern here. That is clamped, simply supported. That is clamped here, simply supported there. So that is why they share the same frequencies. The mode shapes are the same, actually. Okay, let me... that is simply so. So this basic series, of course, is different. This basic series here is simply supported. This, and these are different. Analogously clamped, and these clamped are different. But whatever is left is the same. and frequencies are the same. And mode shapes also could be shown by just mirror imaging that they are the same. Okay, so that's a very interesting phenomenon that occurs here. Oh, time does not go. Okay, no problem. Any questions? Now I would like to address one question that one student had. He had a concern of a student. Okay, so what he says actually is as follows. What I did here, I wrote W of x equals A1K1 alpha x plus A2K2 alpha x, then A3K3 alpha x plus A4K4 alpha x. And then I said that we have some I have to find where I wrote it. Yes, then it will be R K1 alpha x minus L x minus L in zeroth power, okay? And then every time that I differentiated this, I always had x minus L zeroth power. For example, when I differentiated, I wrote like this, W prime x equals. So all of these summations with A sub j times k and whatever indexes are there, alpha x. And then I wrote that it equals R times K4, so first of all alpha, and then K4 alpha x minus L, x minus L0. So the concern was why retain x minus L0, something like that. I think that was a concern. But let us imagine that we have x minus L in fifth power. So that is what we taught in strengths of materials. And we said that derivative of this, ddx, equals 5 times x minus L 4. So what he wanted actually, the student, I assume, he wanted somehow us to differentiate it as a product maybe or something like that. Why? But here also actually we write down what is this x minus L in fifth power. This is like x minus L in fifth power if x is greater or equal than L, 0 otherwise. So we can differentiate then this function, ddx of x minus L in fifth power equals. So here I'm differentiating 5x minus L in fourth power, x greater or equal than L, and that is 0. And then I can observe that this could be written as 5 times right-hand side can be written as 5x minus L in fourth power. But this also can be written like this. It equals, but also can be written 5x minus L in fourth power, x minus L zeroth power. That is also perfectly okay. We could also written like this. X minus L in fifth power, x minus L0, first derivative, equals x 5 times x minus L in fourth power, x minus L0. Okay, we can also maintain this. Both are correct. This is x minus L in fifth power, and this guy is 5x minus L in fourth power. So actually in every representation we did the same. Just here symbolics is more convenient, so to say, when we deal with polynomial functions. But it could be non-polynomial function. Let us imagine I have such a function, sine x times x minus L0, and I would like to calculate the derivative. So what is this function? Sine x minus L0. This is sine x if x greater or equals than L, 0 otherwise. So let us differentiate that. d dx of this function will be naturally from here, from the right-hand side, will be cosine x if x greater or equal than L or 0 otherwise. So then we get actually d dx sine x minus L0 equals cosine x and times x minus L0. So this x minus L0 came there naturally. It is like a label. Like, for example, it says Nikes. It just says where function is 0, where it is not 0. So concern, I hope, should not exist anymore. Okay, no concern. Okay. And now results for some results for multi-span beams. So imagine I have such a beam now. So that is L, 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 etc. And this is L also. So we have, say, N span beam. Okay? N span beam. And imagine that this beam is simply supported and another beam like that is clamped. So L, 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 etc. We considered these beams, we studied these beams for such systems for Kennedy Space Center. Some years ago. What happens is as follows there. So there is a space shuttle, okay? But the space shuttle should be protected before flight also, in order not to be damaged by some panels. And these panels were made like this, multi-span panels. And also, we did not want these panels to be damaged during the takeoff. No damage during takeoff. So we had this grant here at FAU from Kennedy Space Center. And actually, we wrote a book. They allowed us to summarize it in a book. It is called Probabilistic and Convex Modeling of Acoustically Excited Structures. If you want, there is many multi-span systems, etc. It is available in the library. And what happens here is very interesting. First of all, here, for that is called simply supported, that is clamped. Simply supported N-span beam has N series of frequencies. Okay, one series is first basic series, and that is simply supported single span beam. Beam's frequencies. And n minus 1 non-basic series. Okay, non-basic series. Now, clamped n-span beam has also n series of frequencies. First is a basic series. That is a clamped single span beam. And n minus 1 non-basic series. Okay. Then this n minus 1 non-basic series coincide in both cases. They share n minus 1 non-basic series. N-span structures. Yes. Say it again. N minus 1, yes. There is one is basic and the rest is non-basic. So there is in total n series. So, for example, a simply supported 10-span beam has 10 series. One basic plus 9 non-basic. Clamped 10-span beam has also 10 series. One basic plus 9 non-basic. Okay, so that means that these 9 non-basic and these are the same. So clamped, simply supported, and clamped, 10 span beams share 90% of all frequencies. Okay, so that is a conclusion. 90% of frequencies are the same. Any questions here? Okay. No questions. Let us go to something else, another topic now. Totally different topic. What is our topic number? 35? Inhomogeneous structures. These are structures in which either E or ρ or H functions of space. Means E is a function of x, of I is a function of x, A is a function of x, then rho is a function of x. So in most general case, all of these are variables. Then differential equation will be like this. Not as we had for uniform structures like this. E, I, D for W dx in force power plus rho A d2W dt square equals 0. Not this equation, but like this. d2 dx square EI d2W dx square plus rho A d2W dt square equals 0. Because this is an expression of the moment. And what is written here is that derivative, second derivative of the moment equals the distributed load. Okay, so that is, this term actually belongs to a Frenchman, D'Alembert. 19th century, he says, from static equations, you can make dynamic equations if you add inertial terms. One can get dynamic equation from statical one by adding an inertial term. Okay, so that is like, this is F, and that is like MA, okay, in Newton's law. But that is called D'Alembert's principle. Why it is called principle? Because it cannot be proved. It cannot be proved, so to say, by some generic considerations, because every time this term is different. It depends on the physical context, etc. So there is no single term. It is called D'Alembert's principle. Now, one can actually prove that this is correct. That this particular expression is correct by obtaining vibration equation for the beam by something that is called Hamilton's principle. But then we will obtain this term. But why adding a priori this term is correct, we cannot prove. It just turns out to be right. Any questions? Or maybe we will talk, student is asking whether or not from this equation so-called D'Alembert's operator is obtainable. We will talk later, but for our purpose, that will be not pertinent. I'm just saying that this term we also had before for the uniform beam. Now, what we are changing is just this expression. And then the question, of course, arises how to solve this vibration problem. Question, how to solve this equation 1, okay, this equation 1. So, okay, something can be simplified. This is partial differential equation. So we can write Wxt equals capital W of x sine omega t. This is omega. I substitute here, I get d2 dx square EI d2 capital W dx square minus rho A omega square W equals 0. So, or more specifically, d2 dx squared e of x, I of x, d2w dx squared minus rho of x, a of x, w equals 0. Okay, how to solve this problem? E is E, I, rho, a, given functions. No general exact analytical tool. Okay, so that does not exist. There is no one method that could solve this problem. So therefore, if someone wants to dedicate himself or herself to this problem with promised Nobel Prize, he or she is most invited. There is no one analytical method that you would use it and for every case will produce a solution. Now, yes? Can you speak louder? Yes, omega square, of course. You are right. Student tells me that I forgot omega square. He's right. So now, of course, there are approximate methods. Many approximate methods. So like FEM, finite element method, finite difference method, etc. And we know one method already that could solve this problem also. What it is called? Galerkin method, of course, can. But this is an approximation, not more than that. Only an approximation. Now, there are some lucky cases of exact solutions. Okay, and we will describe some of them, some lucky cases. And that means, why do I mean lucky? Either random or non-random hitting upon the ball of exact solution. And I will describe some of these. Okay. Okay. First, Euler's, that was 36. Euler's exact solution. Okay, Euler did himself, 1759. He says as follows. If EI is a function like this, d sub 0, a plus b, x over L in power m. Okay, imagine this is a solution. This is a problem. Then for m equals 2 and m equals 4, buckling load, I mean this is buckling. So that means that what we have is as follows. EI d2w dx squared plus P critical W equals 0. So that is an equation that he used. So he said P critical equals, look please, d sub 0 B square L square pi square natural logarithm of A plus B over A in power minus 2 plus 1/4. That is from m equals 2. And okay, so he obtained the exact solution. Okay, so that is some function, but this is a function, not any function. So P critical here equals pi square d sub 0 A square A plus B square over L square for m equals 4. So that is 1759. Okay? Then we are waiting until 1893. Engesser. That is from Germany. So what he has is as follows. Look, please. He says EI d2w dx squared plus P critical W equals 0. He says if EI equals like this, 4d sub 0 x L minus x divided by L squared. So that is his expression. So let us calculate what it is. That is 4d sub 0 over L squared xL minus x squared. Now he says if you substitute W